Okay, hello. So here we are. We're covering, and I have a spelling mistake. We're covering review 8. We're just getting started today and we'll finish on Monday. But it's estimating area under a curve using rectangles, also called Riemann sums. You'll hear both used. And so here goes. Um, if you would look for trends as we go, it would be great, but we're going to start off with the easy part, which is finite, and then build towards infinite and probably finish infinite on Monday. So if I'm going to draw x squared plus 1, which is a parabola, which really grows fast, but I'm going to graph it really wide to help me graph this a little better here. If I use 4 rectangles from those two things, and the fact that we're using equal subdivisions, we can tell how wide each one is. Remember, delta x, or the base of each rectangle, comes from the region width divided into however many chunks. So in this case, dividing it into 4 makes each chunk 2. All right. Now, depending on how you organize the rectangles, we typically focus on left, right, or midpoint. You'll get different estimations. If I use LRAM, it's the sum of bases times heights, where the base is delta x and the height is f at different points. You're using 4 rectangles, so it looks something like that. Now that's great. I'm just trying to lay the groundwork for sigma notation, which we use on infinite quite a bit. But if you didn't show that, that's okay. If you went straight to, I'm going to take out the equal subdivisions of 2. Now I am picky in that I don't want you throwing numbers at me inside. I want you telling me what you did to get the heights. If we're using LRAM, then in the first subdivision, I go to the left endpoint, go up to the curve, and draw my height back across. So the first height is f at 0. Because this is review, then I think you know then that your other heights would be that. That said, then you try what RM is. Don't worry about the summation notation, just give me the expanded notation. And, sorry, MRAM. Probably not a lot of room to work, sorry about that. Okay, so if you know what you're doing, somebody give me RM, and I assume you would say, if you were actually in my class, f at 2 plus f at 4 plus f at 6 plus f at 8. Those are the right edges of each subdivision. And MRAM, it's the middle of each subdivision. So halfway between 1 and, or 0 and 2 is 1, f at 1, f at 3, f at 5, and f at 7. All right, now the best case, the easiest case is equal subdivisions. Sometimes, and especially long in the days before calculators, if you wanted area under a curve, sometimes the subdivisions weren't pretty. For example, if I divided this into 4 parts, doing it in 4 equal parts is going to be fine for 2 places like 4 and 16, but not so much for 8 and 12. So because of that, you would typically then use unequal subdivisions. For example, you'd be choosing marks where you would square root nicely. So some numbers that square root nicely are 1, 4, 9, and 16. And because that's unequal subdivisions, the idea of factoring out a delta x as a greatest common factor is not going to happen because there is no common factor. That's a no. And so for unequal, you have to find each separately. Delta x1 is 1. And the first height is from 1 to 4, which is a 3. And if I used LRAM, then I use the height at the left edge 1. So it's 3f at 1. Plus the next delta is from 4 to 9. It's 5. You see the trend there. It's 5. The right endpoint from 4 to 9 is 4. And the last delta x is 7. And the left edge is 9. So 7f at 9. Now, in all these cases, I don't really give a rip what they equal. I just want them set up. You can find what they equal, push come to shove. I'm not worried about the answers to this. We're just talking conceptual right now, all right? So don't worry about finding the answers. I know that feels wrong. You try RRAM, and notice I didn't ask for MRAM because the midpoints in those are not going to be pretty, and that kind of defeats the whole idea. So just RRAM. All right, so I hope you saw that the bases are the same. It's the heights that'll be different. Using the right edge, we do f at 1, f at 4, f at 9, and f at 16. For the question in, why is your answer to B, to A, an underestimate? So when I say A, I mean left hand. Why was LRAM an underestimate? And so saying it well is important to me. Students, layman's terms, want to say, well, because the rectangles are under the curve, and that's true, but it's not very mathy. And so let's talk more. Why are they under the curve? Well, they're under the curve because we're using the left edge on something that's increasing. If it's increasing, then the left will be the lowest possible point on the curve. And so we would say, if you're going to say this well, you'd say the answer in A is an underestimate because we used LRAM on an increasing function. And the stars of the show would be the combination of LRAM and increasing. That's what I would underline. If I were grading your test, those are the two things I would be looking for, along with obviously the conclusion that it's underestimate. If then I said working from a table, estimate the area under this using 4 rectangles. And it doesn't say, but we're going to use equal subdivisions here. LRAM, RM, and MRAM. Again, just set them up, but don't worry about the answer. That's not important to me. Now, I technically could use 8 rectangles for A and B, but it says use 4, so I'll use 4. And I'm getting then a delta x of 2. It's an equal base, so I'm factoring that out. And then my LRAM, or my heights rather, are f at 0, f at 2, f at 4, and f at 6. RM, if you haven't done it already, do that one. Okay, so it's the same base, 2, and f at 2, f at 4, f at 6, and f at 8, and MRAM. Okay, the midpoint of each is 1, 3, 5, and 7. Okay, and then you get your answer, and that's good. But that's what I want to see is that where did you come from kind of thing. Now, working towards a little more abstraction here, express the area under the curve starting at a left endpoint at x equals 0 using right-hand rectangles. So this is the easiest case. When we start at 0 and we are doing right hand. If I wanted to do this then in a more abstract way, instead of using an exact number, but more of an abstract or any type of number of rectangles, then I would start by finding delta x, and I know the region width is 8, but I don't know how many subdivisions, so I don't really know how wide each one is, other than 8 divided by whatever I choose for n. Yeah. Now, a picture helps a lot, and keep in mind that the goal is to look for patterns. I'm looking for patterns. So if I had this curve here, the first delta x I go over would take me to 8 over n. The next one would be 16 over n, but it might help to think of that as 2 8 over n's. The next is 24 over n, or 3 8 over n's. And so if we're to generalize, the ith rectangle is I 8 over n's. Now those are the marks at which I'll draw my heights. The base is the same each time. The base is 8 over n. What's varying is the x at which I land, okay? So when I go to do this, if I did this with RRAM, as we said to do, the base is delta x, and it's 8 over n. The heights are, well, the first height is the function at 8 over n. The second is the function at 16 over n, or 2 8 over n's. The third height is f at 3 8 over n's, and so on. Generally, the height is the ith 8 over n, and so on. The last mark, well, it would be the nth 8 over n, and the nth 8 over n is just 8, yeah? So these are f at different points that come from taking f at multiples of 8 over n. So in summation notation, if I were to express this, it's delta x for the base times f at different points for the height. That's pretty much the universal. As far as how many rectangles, because we're using right rectangles, the first height is at 1, and the last is at however many rectangles you use. And that's general. Now I'm going to go a little more specific. In this case, delta x is 8 over n. Inside, the x at which I draw is 8 over n I times. Now I'm going to go a little more specific. In this case, the function is blank squared plus 1. And so inside is the 8 over n I times that guy right there. That's what I'm putting into the function each place in terms of x. All right, so when you set up a summation notation, you'll have a delta x out front, which comes from the width of the region divided into n chunks. Then inside, you're going to have the function shell, blank squared plus 1 in this case, at different marks along the way that come from how many delta x's you've gone over before you went up to the curve to find the height. I hope that makes sense. You try, write an equation and a summation notation, I mean, to estimate the area under f of x equals root x plus 1 from 0 to 2. In essence, I want you to redo this work. Okay, so if you start here, this, like I said, is pretty much the universal, assuming you're using right-hand rectangles. And yet I do want you to write it. It's just, it's good calculus, and that's where the fundamental theorem is eventually going to flow from there. Now for this case, the summation stays, but we'll change as delta x. Now because the region's only 2 wide, I'm going to have a 2 over n. And so the x at which I draw, x sub I, will come from 2 over n however many times, and that's where the counter. Remember, we're trying to add many cases of a pattern. The I is the pattern maker, and the sigma is the sum. And now, if I just use the function, in this case it's root blank plus 1 square rooted, and in that blank goes that 2 over n 5 times. Now, if you really understand this, then you should also be able to go backwards. So flip it over now, and we're going to probably do this and then stop. This time, instead of giving you the area, describing the area and asking for the summation, I'm giving you the summation and asking for the area. We'll try one together. In this case, let's just, again, assume it's starting at 0. I'm going to go there first. This tells me how wide the region is. And so because it's 3 wide, that tells me that the region must be from 0 to 3. This, that 3 sub n, that delta xi times, this is the x sub I. And so the rest of it must be the function. And so the function is 2 minus x cubed. That's the idea. Sorry about the lack of room. You try the next one. You try, and we'll stop there. Okay, so assuming it starts at 0, which is an assumption we'll talk about later, and it's 5 wide, which comes from that, then the region is 0 to 5. This here, each time you see that delta xi times is an x sub I. So if I look at what the function is, it must be the case that the function, and I'm calling it f, I'm assuming, I'm just going to give it its own name, is 2x cubed plus x. Now, I hope you did well, and if not, we'll go over it Monday, but that's it.